this problem, we have a rocket that is launching upwards. So there's the rocket. It's going to launch upwards from a launch pad. Upwards is the positive direction. So the first thing we need to know that we need to take the velocity relative to the launch pad. And so that would be m times this by dv relative to time plus would be v times this by the mass relative to time, right? And then we set this equal to the actual velocities acting on the rocket. Now, so this would be negative because the rocket is pushing off of the ground. And so we have the velocity of the rocket itself, which we just call v, minus the velocity of the exhaust. That is pushing against the ground as well. So it would be negative in this case. Times this by the mass going out, d of the m, or mass going out, over dt. This would be the first part of our equation. So we can recognize that m is equal to the initial mass of the rocket, which is the mass of the rocket itself and the fuel added. We also have to know that over time, after the rocket launches, fuel is being used up. And we'll call that variable f of c, the fuel consumption. And over time, more fuel is being used up. And so that amount of fuel is being subtracted to m naught the more time passes. And so we can plug that variable in place of this m right here. So you have m naught minus f of c t dv over dt plus v dm dt. So you set this equation equal to dm dt. You can get rid of this variable and this variable. You're left with negative fc. So that's exactly what goes in place of that. Negative fc. And then equal to the same thing here, v minus v of the exhaust. And now since this is dm dt, but the mass is actually the mass going out, this would make this value negative right here. But since we are plugging negative fc in place of this, it would actually be positive in this place. And so we can simplify this side right here. We get negative fcv plus fcve, right? And then you also notice that negative fcv is also on this side, so that means we can actually cancel these out. And on this side, all we're left is with m naught minus fct dv dt. And so now we just need to isolate dv dt. We need to find the change of velocity to respect the time. So we do that, we get dv over dt, that's equal to f of c times by v of e, the exhaust velocity, or the exhaust velocity, divided by m naught minus f of c times this by t. Here's the point where we can actually set up an integral to get the expression for the velocity of the rocket. So what we do, we can multiply both sides by dt, so that we get rid of dt on the left and move it to the right. So we do that with this equation. So we can set up the bounds of integrals. Now what are the bounds? So the bounds, we'll just call it 0, start at 0 velocity and get to a certain maximum velocity. Same with this. We start at a time of 0 seconds, go to a time of t, whatever that t is. So with these bounds 0 to v, dv will just be v, right? And so we can see that we need to recognize that fc times ve is actually a constant. So we can actually move that outside the integral. And with this, we can actually perform u substitution. U in this case would just be m naught minus fct times this by, or not times, du would be negative fc times this by dt. Negative more clear. And so we do this, fc ve 0 to t 1 over u, and dt would become du over negative fc. What I was doing. And so we can divide fc by negative fc. You just get negative 1, and fc's cancel out. You're left with negative vv times this by the natural log of u with the new bounds, and you multiply, you set t equal to 0. Bottom bound will be m naught, and t is just t. For the top limit, you get m naught minus fct, right? And this is all equal to v still. For the final part of this expression, right, we will have I already lost my place. Negative VE, and so we can actually make that positive, but that will actually flip the bounds upon each other, right? So this is going to be positive VE times this by the natural log of m naught over m naught minus fct, and this right here is the rocket equation we're asked to develop from the beginning.